Alright, there's 3 parts to today's lesson. Alright, there's 3 separate parts that we're going to do. First part is the remainder, second part is the factor theorem, and then the third part is actually 4.9. Okay, so there's actually 3 parts to today. The first one is your remainder theorem. Everybody got the title down?
Yes.
Fantastic, moving on. Okay, now all you really need from this slide is summarize the bottom, because there's a vocab word in there. It's highlighted in yellow. It's called synthetic substitution. Okay, so basically what the remainder theorem states is that you can evaluate a function by, instead of plugging that number in to the function like you guys just did, you can set up a synthetic division with that function and with that number. Alright? It is a shortcut way to do it. At least I think it's a shortcut way. There's mistakes that could be made here, which is why I don't ask you a whole lot of questions about it. Because just like with evaluating functions, there's still mistakes that you can make. Okay, so it's not like it's a foolproof way, because there's still places you can mess up. This is the oddball, alright, because you guys are going to realize today we're going to take synthetic division and apply it to 2 different cases. These first 2 lessons is what that, or parts of the lesson is what that's about. Alright, synthetic substitution, convenient way to find the value of a function, especially when the degree of a polynomial is greater than 2. Okay, so the one you guys just did was with a degree of 2, right? You had a squared, and then you had a 5x, and you had a 4. Okay, make keep it there for a second. So the function you have is negative 3x squared plus 5x plus 4, and we said find f of 3, and you guys said that was negative 8, right? Here's what else you could do. Instead of plugging that 3 in, you can set up a synthetic division. Negative 3, 5, and 8. And then in your box, you can put 3. Bring the negative 3 down, gives you negative 9. Negative 9 plus 5 gives you negative 4. Negative 4 times 3 gives you negative 12. Oh, I screwed up. I wrote the 8 instead of the 4. I was like, wait a minute, this ain't right. 4, there we go, which gives you negative 8. Everybody see how that works? So what you can do is, instead of plugging that number in, you can synthetically divide with that number, and the remainder is the same as if you had plugged it in. Okay? Now you can argue which way is more efficient, which way you're less mistake prone. I get all of those arguments. The main argument I have that's pro synthetic substitution is, imagine if you're going to the 5th power with some of these functions. 6th power, 7th power. You would be plugging that 3 into all those powers, taking it to all of those exponents, multiplying by all those coefficients, have huge numbers, and then add them all together. Like I said, I realize that it's not mistake-proof throughout, but it's a pretty neat trick. Okay, at least I think so. And classes prior have thought so too. They're like, oh, that's cool. Everybody good here? So here's what you do. The number that you're evaluating at, so 4. And here's where this is the trickiest part to this. This is the only time in synthetic substitution that you don't switch that number. Okay, this one's the oddball. So if you're going to default to one or the other, always switch the sign. But this type here, you don't. Okay? But if you have to set your mind on one, set it to switch, because then you'll get 2 out of the 3 problems that you do. But this one you don't. You still go set up your synthetic division the exact same way. Pay attention to missing powers. So we have 3, negative 2, 0, 5, and 2. There's a missing x squared.
Is there always something missing?
Nah, not always. Bring the 3 down. 3 times 4 is 12. Add the 2, that gives you 10. 10 times 4 is 40, not 44, whoops. 40 plus 0 is 40. 40 times 4, 160. 160 plus 5 is 165. 165 times 4, I believe, is 660. And 660 plus 2 is 662, and that's your answer. Okay. Like I said, it's not mistake proof because you could accidentally flip the sign on this one even though you're not supposed to. You could forget the 0 because that still needs to be there. I get that part. Okay. This is just one of the applications to synthetic division. But imagine how much more, I mean, you're still working with the numbers. You know, your numbers are still fairly large. But imagine the work if you were going to plug this 4 in here 3 times. Take it to the 4th, have to write out every single line. Whereas here you just do this little dance and you get your answer. Okay, make sense? So the second one, same way. -1 and then 4. We're missing the 4th power, so we need a 0. 2, 1. We're missing the 1st power, so we need another 0. And then -1. So 4 times -1 is -4. Yeah, it was 0. Positive 4, which gives you 6. -6 gives you -5. Positive 5 give you 5. And then -5 to give you final answer of -6. Okay, that's part 1 to today's 3-part lesson. Pretty easy, pretty simple. Okay, part 2. Part 2 is called the factor theorem. All right, part 2 is called the factor theorem. Now, as you guys are looking, here's going to be an example of a factor theorem type question. So, you're going to be given a polynomial and then dividing by a binomial. So now we're going back to our first way of synthetic dividing, which is your most common way. So everything there holds true. So in your box is going to go -3 this time, okay? Like I said, if you have to remember one way or the other, remember to switch the sign. Okay. Now, I have a question before we move too much further. If I asked you guys, like, list the factors of 36, what would you say?
72. No.
No.
6.
Wait, is that like 6 and 6?
6 and 6.
12 and 3.
12 and 3. 1 and 36.
18 and 2.
18 and 2.
36 and 1.
36 and 1. I think that's all of them, ain't it?
Yeah.
I think we got them all.
Pretty sure.
If not, you get the point, right? It's a pair of numbers that you multiply together to make a number, right? Okay, those have been factors. Remember factor trees? Right? You factor a number down to its factors, the numbers that you multiply together to make that number up. Now we're going to put on our big boy and girl pants, and we're going to do it with polynomials. Okay? So to figure this out, to start with, they give us one of the factors. They tell us, or at least according to the theorem, they're going to tell us that x plus 3 is a factor. Why? Because you get a 0. Right? Divide 36 by 12. What do you get?
3.
You get 3. Not 3 point something something, not 2 point something something. You get 3, remainder 0. That's how you know that 12 is a factor of 36. Same thing here. You get 0 as a remainder, which leaves you with this polynomial as your leftover part. That polynomial is called a depressed polynomial. It is a polynomial that is the result of dividing a polynomial by one of its binomial factors. Okay, so if you divide, just much like a number, if you divide a number by one of its factors, your remainder is 0. If you divide a polynomial by one of its factors, its remainder is going to be 0. So with this type of question, your remainders have to be 0. Okay? Any questions this slide? Everybody good? See a lot of pencils moving, so here's your question type for these. Determine whether x minus 5 is a factor of x cubed minus 7x squared plus 7x plus 15. Then find the other factors of the polynomial. So you set this up with a synthetic division. Alright, the binomial is x minus 5. We go back to switching our signs, which means in our box is going to go 5. You line up your coefficients. 1, negative 7, positive 7, and 15. We bring down the 1. 1 times 5, 5. Negative 7 plus 5, negative 2. Negative 2 times 5, negative 10. 7 minus 10, negative 3. Negative 3 times 5, negative 15. Plus 15, 0. Your remainder is 0. Which means that x minus 5 is one of the binomial factors that make up that polynomial. Yay, that's half of it. The other half is finding the other ones. Here's how you do that. Write your depressed polynomial out. Okay, write your sad polynomial. X squared minus 2x minus 3. And we're trying to find the rest of the what? See what I tell you. We're trying to find the rest of the remaining. Ryan trying to find the other factors, right? Which means if we're going to try to find the factors, we should probably take our depressed polynomial and factor it. Because lo and behold, by golly jeepers, maybe it factors. So what does it factor to? X minus 3, that was a terrible 3. X plus 1. There are your other two factors to x cubed minus 7x squared plus 7x plus 15. Okay? Let's take this up one notch. Question. Couple this up with x minus 5. If you were to go through and FOIL all these, what do you get? You get that, right? X cubed minus 7x squared plus 7x plus 15. Because those are the three parts. They just went out again. See, they're weird. Those are the three parts that you multiply together to make that that polynomial. So can you check yourself? Yes, you can. Do I recommend it? It's a little bit of work. All right? I would get good at factoring. Okay? Does that make sense? This is since we're getting to the end of this chapter is, honestly, it's somewhat beautiful because we kind of take everything and kind of tie it all together and play connect the dots with everything. And it's kind of cool to watch. All right? You'll see. Okay? Everybody good? Next one. This is for you. All right? Determine whether x minus 2 is a factor of x cubed minus 7x squared plus 4x plus 12. Then find the other factors of the polynomial. What goes in your box? 2. Okay. 2 in your box. So we got 1, negative 7, 4, and 12. Bring down the 1. 1 times 2 is 2. Add, you get negative 5. Times, you get negative 10. Add, you get negative 6. Multiply, you get negative 12. Add, you get 0. Okay? I will tell you guys this. If you don't get 0, it's not because it didn't. You'd say it's not a factor. It's because you messed up. Okay? You will get 0 every time with these problems. All right? So, write your polynomial. So, x squared minus 5x minus 6. And that guy factors how? X minus 6. X plus 1. Zip. remember when you did synthetic division and we rewrote our answers from problems? And you go from 1 to 1 exponent less, so we start with x cubed, so these go x squared. That's how. Okay. All right. Everybody good? That is essentially the end of part 2, but I'm going to beautifully segue from part 2 to part 3. Okay? And part of that beautiful segue is this. Let's take this same problem. Let's throw in our factor of x minus 2 that they tell us from the beginning. And I'm going to say equals 0 now. And I'm going to make it look like a 0. There we go. And then I'm going to say solve it. So your exponent is 3, so how many answers should we have? 3. And those 3 answers are? Six, -1, and 2, right? Okay. Now, just like I said, we're playing a big game of connect the dots here. These are called solutions. We've always known them as solutions. Specifically, since these are equations, what other vocab word from some point this semester that's probably going to be on your final exam or in the lesson here coming up are these?
Roots or zeros?
Which one?
Roots.
Good job, Shields. Roots. These are your roots, since they're equation. Zeros are when they have to do with what?
Zeros.
Nope.
Graphs?
The graph. Okay? You're going to miss the beautiful part, Maya.
Bye, Maya.
It's okay. Roll them good.
Okay.
All right? So, your last part, 4.9. Roots and zeros.
Ew. Oh.
It's a lot up there.
Oh, this is the one that you said that you personally liked, right?
I'm going to get them, okay? First off, the words to this, we don't need them. This all makes much more sense with an actual example. Okay? This is where we're going to play a big game of connect the dots, connect everything we've learned, see how it all makes sense and connects. Okay? Here we go. Your function that we're working with for this specific example is x to the 4th plus 2x cubed minus 7x squared minus 8x plus 12. When you go graph that, that looks like this. Okay? Leading coefficient on this graph is what? Positive or negative? Positive. Okay? Is it an odd or even degree? Even degree. Even degree because it points in the same direction. Positive leading coefficient because that direction is up. Right? 1, x to the 4th, right there. How many zeros does this guy have? 4. Okay? And if you look off here to the left, it says those zeros are -3, -2, 1, and 2. Because that's where the graph crosses the x-axis. Good. Look down here. -3, -2, 1, and 2. Notice that it's in function notation, so it's talking about the graph of the function. So that's why they say zeros. Everybody good there? We're going to check that one off. Done. Let's go.
When you did that, the lights went out.
Magic. Next one. Notice how the polynomials now equal 0, which means you would have to do some things that we did earlier with given a factor, divide, find the rest of them, right? Okay, part 2. You would still end up with the roots being the same 4 numbers, right? -3, -2, 1, and 2. Does that make sense? Great. Nope, not this time. Let's skip down to the last part, or the bottom one. The x-intercepts of the graph. Okay, so now instead of saying the zeros, they're calling them intercepts, which means it's going to be coordinates now. Same 4 numbers. -3 with the 0 as your y value. -2 with the 0 as your y value. 1, 0, 2, 0. Does the last one make sense?
Yeah.
Great. here's the one you need to worry about. And you've honestly already done these before too. You did these in chapter 3. We wrote quadratic equations when we were given the zeros, or given the roots. I'm pretty sure it said write the quadratic function given the following roots. And we did things like 2 1/3, or stuff like that. Alright? The factors of that polynomial come from the zeros or the roots. But the factors, if they're going to become that way, have to be, number one, in binomials because you're going to FOIL them out, right? And secondly, if you're going to get your zeros from them, they have to equal 0. Hence why these numbers go to -3, and then your factor of it is x plus 3. Okay. Does that make sense? Yay or nay?
Yeah.
Yay? Okay. So, here's where this leads us to. Okay, we got 3 more slides. Mine's in a little different order, okay, so play along with me. So, what this leads into is this. We're going to take zeros now, and we're going to write the functions, write the polynomials. So, write a polynomial function of least degree with integral coefficients. All of that just means make it look pretty. Okay? No fractions, no random degrees, no extra stuff. Just make it look good. The zeros of which include -1, 4, and -2. So your steps to these are very similar to when we did them with quadratic equations. You would go x equals -1, x equals 4, x equals -2. You would then take them from their zeros, turn them into their factors, which means move them from the right to the left, and put them in parentheses. X plus 1, x minus 4, x plus 2. With quadratics, all you would have to do is FOIL, because there's just 2 binomials, right? Here you have to multiply, FOIL, and then multiply again. So it's a 1 extra step on this one anyways. So pick 2 to FOIL. I usually start on the left, okay, except for a specific case, you'll see that next. So start FOILing. X times x is x squared. X times -4 is -4x. 1 times x is x. 1 times -4 is -4. That also needs to be multiplied by x plus 2. You got like terms in here, clean them up. So x squared minus 3x minus 4 times x plus 2. Turns it into a trinomial times a binomial problem, which you also know how to do from the first section of this chapter, so start distributing stuff. X squared times x is x cubed. X squared times 2 is 2x squared. -3x next into the binomial, so -3 x squared minus 6x, and then -4 into the binomial. -4x minus 8. Go through and get your like terms one last time. So x to the third minus x squared minus 10x minus 8. And that's your answer. Before you write down that, before I explain that, I got a question for you, okay? X squared plus 49 equals 0.
X plus 7, X minus 7.
Nope.
7.
Close.
X plus 7.
You have to move the 49 over, right? Because that left side don't factor.
X plus or minus.
7i, right? Okay, because you took a square root, right? And you got a plus and minus because you took a square root. And then you got an imaginary because when you took that square root, it was negative, right? Now, imagine that going backwards now. Okay? Imagine this going backwards. Let me write it twice, though. So x equals 7i. Oops. X equals 7i. X equals negative 7i. Imagine this going backwards. You would subtract the 7i over, you would add the 7i over. You would FOIL it up. You would end up with this. Okay? Now, here's my question. How do you know how to get rid of an I? Think back.
Square. I is a negative 1, isn't it?
Almost.
Is it just a negative?
Not I.
I thought it was I squared.
I squared.
Squared is negative 1.
I squared is negative 1. For the most part, that's the only way you guys have known how to get rid of i's. Okay? So, in order to get an I squared, how many i's do you have to have? 2. There's 2 here. There would be 2 if I gave you x squared plus 36. There would be 2 if I gave you x squared plus 64. Because they all come from square roots. Right? And anytime you take a square root, you put in.
9. Or no, plus minus.
Anytime you take a square root, you put in a plus or minus. If it's a negative square root, you put in the I. Right? So that means that imaginaries always happen in what? And? I'm thinking of a P word. Nope. I's happen in pairs. They always happen in pairs. Specifically, one positive, one negative. Right? Because you go from plus or minus. That's what this all says. Okay? If a plus bi is going to be a 0, a minus bi is also a 0. Automatically. Okay? Automatically. Otherwise, think about it. If you didn't have its partner, you wouldn't have 2 i's. You need to get 2 i's in order to get rid of it. If you don't have 2 i's, you don't get rid of it. Plain and simple. So here's how this one will look. Last one. Same pretty much setup. Okay, same words as directions. Polynomial function, least degree, integral coefficients. Zeros of which include 2 and 4i. Now, they tell you 4i is a 0. What they don't tell you is that its conjugate is also a 0. That's what you need to put in. So since they give you plus 4i, you need to put in minus 4i. You add that in. I don't. You do. Okay? After that, the process is fairly similar with a little slight twist. Next step, still making binomials. So move them over. So x minus 2, x minus 4i. And this one becomes x plus 4i. Alright. Now, the first one, I foiled the first 2 together first. That's because they were on the left. This one, I'm going to foil these 2 together. Your i's. Alright? As you always should, because it's going to make your problem a lot easier. Alright? There you go. So we have x minus 2. Because these 2 are what? Complex conjugates. Good. So maybe we will do good on the final. Complex conjugates, which means these 2 are going to end up having no i's. Okay? So FOIL it out. X times x. X squared. X times 4i. 4ix, good. Negative 4i times x, negative 4ix. All right, now, negative times positive gives you negative 4 times 4 gives you 16. I times I squared. Now, I wrote this out just so you see it. See these two? A 4ix and a negative 4ix. If these are in your answers, you did something wrong. Okay? If these end up in your answers, you did something wrong. Thankfully for us, 4i minus 4i gives us 0. And 0 times x is 0. So those middle two terms, as they should, cancel. I squared is what? Negative 1. Remember how I said I squared equals negative 1 is the most important thing from that i's? This is why. Negative 1 times negative 16. And then all it's left to do is FOIL it one more time. X squared times x. X cubed. I'm going to do it in a different order just to put them in standard form, okay? X cubed minus 2x squared plus 16x minus 32. Page 290, 14, 15, 18, 20, 22, 23. And then page 298, 39 through 42.